Hi, this is Brooke Hollingshead. This is my third video presentation for Math 510, Applied Linear Algebra. This presentation is about linear transformations as they relate to vector spaces. So the first thing I want to do is kind of give a loose definition of a linear transformation as it applies to a vector space. Basically, it's similar to a function that would map from one entity to another. So in previous lessons, we've talked about mapping from reals to complex numbers, or from 2 dimensions to 3 dimensions, or from vectors to scalar numbers. So basically what we're doing for this one is we're taking from one vector space to another vector space. As long as it qualifies from a vector space, we're going from one to another, or we can actually go back to the same one. So it's just some way to map, take one vector from one vector space to either another vector space or back to the same vector space, as long as they qualify as a vector space. So there are two main properties that it would need to qualify as a linear transformation. So the way we would write a linear transformation is the transformation from one vector space to another vector space. Again, this could be back to the same one, but as long as they qualify as a vector space and hold all the properties of a vector space, we're taking from one vector to another one. The two properties that we would need are scalar multiplication. So I need to be able to multiply. If I take a transformation of a vector and I have multiplied it by a scalar number, I need to have that be the same thing as taking the scalar times the transformation of that vector. So that's the first property. The second property I need is vector addition. So if I take the transformation of two vectors added together, that needs to hold as the same thing as if I took the transformation of the first vector plus the transformation of the second vector. So as long as those, and some videos and some authors say that we also need to have a third one as vector difference or subtraction, but as long as our addition holds, we can do the same thing for that one. So we'll do multiplication and vector addition. So the next thing we're going to do is apply it to a specific type of transformation. So the transformation we're going to do this to is from R2 to P2, where P is a vector space of polynomials of degree 2 or less. And our transformation looks like this, where we have a1, a2, a1x squared plus the difference of a1 minus a2 times x minus a2. And for this transformation, again, we just have to prove those two properties. So the first one, we're going to do the scalar multiplication. And I'm going to take a scalar times, I'm going to take the transformation of a scalar times vector A, which means I'm taking the transformation of a scalar times every A1 and every A2 for that linear transformation. So I'm going to have, every time I have an A1, I have the scalar there. Every time I have an A2, I have the scalar there being multiplied by it. So this is what it's going to look like. Now if I can go ahead and multiply some things out, and I have CA1x squared, CA1x minus CA2x minus CA2. Now I can factor the scalar, I can factor C out of all of those, and I have A1x squared plus A1x minus A2x minus A2. And then I can factor the x out of this one, and you'll notice that it looks just like my transformation of vector A. A1 minus A2 minus A2. This looks just like transformation of A1, A2, which is then just the transformation of vector A. So we hold under scalar multiplication. Now we have to check that we also hold under vector addition. So if I take, I'm going to let A be A1, A2 like we've been doing, A1, A2 like we've been doing, and then I'm going to let B be B1, B2. So I'm going to take the transformation of A plus B. And if I have, so every time I have an A1, I'm going to add it to a B1. And every time I have an A2, I'm going to add it to a B2. So A1 plus B1. A1 plus B1 minus A2 plus B2, adding the corresponding elements of the vectors together. Then I have all of that times x minus, and then I have A2 plus B2, again, adding the corresponding elements to each other. So I have A1 x squared, when I multiply everything out, B1 x squared, A1, I'll go ahead and multiply all that out while I'm doing this all at once. A1x minus A2x, B1x, B2x, oops, minus A2 minus B2. Rearrange, put all the a's together, put all the b's together. So I have A1x squared plus A1x minus A2x minus A2. Okay, all the a's are together over here. Now, b's together. B1x squared, B1x minus B2x minus B2. I can factor out in each of these, I can get those x's out of the middle terms. So I have A1x squared, A1 minus A2 x minus A2. Same thing on this side, B1x squared. I can factor out that x out of the middle terms. B1 minus B2 x minus B2. Notice that this first half is just the transformation of A, and the second half is just the transformation of B. Therefore, my vector addition is good. My scalar multiplication was good. T is a linear transformation. Thank you.